This lecture is about the types of errors and the ways that you will evaluate the prediction functions that you generate during this class. So first of all, we're going to focus on the types of errors that you can make when you're doing a binary prediction problem. In other words, where you're trying to predict things into one of two groups. In general, we're going to be talking about language in terms of true positives and true negatives and false positives and false negatives. So the first thing to keep in mind is that when we talk about positive versus negative, we're actually talking about what the algorithm decided, whether it decided that you're in a class or not in a class. Then true and false refer to the true state of the world. So true means that you actually belong to the class we're trying to identify, and false means that you actually don't belong to that class. So as an example, the true part of true positive means that you were correctly, so in other words, the truth is that it was something to identify, a positive. In other words, we actually identified you as belonging to that class. Similarly, for a false positive, the positive part again refers to the fact that we identified you as being part of the positive class, and false refers to the fact that you were wrong. We didn't actually classify you to the correct class. To make this a little bit more concrete, consider a medical testing example. So in this case, we're trying to identify people that are sick using, say, a screening test. A very common example would be, say, mammograms to try to identify if women have breast cancer. In this case, the true part will be the status as to whether you're sick or not. So if we say that we truly identified you, then you were truly sick. And if we falsely identified you, then you were actually healthy, you were not truly sick. So in this case, a true positive is truly somebody who is truly sick, and it's positive. In other words, we actually diagnose those people as correctly as being sick. If you're a false positive, it means that false, in other words, you are a healthy person, but positive means we were still somebody that we identified as being sick, even though you weren't. Similarly, with a true negative, this is somebody true who is truly negative, truly healthy, and we identified them as being negative. And a false negative would be somebody who is sick, so we incorrectly identified them as healthy, and the negative part is we identified them as healthy. You can learn more about sensitivity and specificity by going to this Wikipedia link below. You can also see them in this 2x2 table. So it's called a 2x2 table because it has 2 rows here and 2 columns here. So the columns correspond to what your disease status is. So in this particular example, positive means that you have the disease, and negative means that you don't have the disease. That's the real truth about your disease status. And the test is our prediction, or our machine learning algorithm. A positive means we predict that you have a disease, and a negative means that we predict that you don't have the disease. So some of the key quantities that people talk about are the sensitivity. This is the probability that we give you predict that you are diseased, given that you really are diseased. So if you're really diseased, what's the probability we get that right? And then the specificity is, if you're really healthy, what's the probability we get it right? The positive predictive value is the probability that we call you diseased, or probability that you are diseased, given that we call you diseased. So it's a little bit different than the sensitivity in the sense that now it's looking at all the people we called diseased and saying what fraction of them actually are diseased. Similarly for the negative predictive value. And the accuracy is just the probability that we classified you to the correct outcome. So in this table, it's the terms on the diagonal, it's the true positives and the true negatives, just added up. So you can write these as fractions. So for example, the sensitivity, that's the probability, given that you are diseased, that we called you diseased. So we look at this first column. This is all the people that are diseased. And we look, what fraction of them did we actually get right? So that's the true positives divided by the true positives plus the false negatives. That gives you the sensitivity. You can similarly make the same sort of fractions for the specificity, the positive predictive value, the negative predictive value, and so forth. When looking at the positive predictive value, we basically look at in this case, it's the true positives divided by the true positives plus the false positives, because we're looking at only the positive tests, and we say what fraction of the positive tests did we get right. So the true positives were the ones that we got right, and the true positives plus the false positives is the total of the positive tests. So this is kind of important because many prediction problems, one of the classes will be more rare than the other. So for example, in medical studies, it's very common that only a very small percentage of people will be sick. In this case, suppose there's a disease where only 1.1% of the people are sick in the population. And suppose we have a really good machine learning algorithm, a really good testing kit that is 99% sensitive and 99% specific. In other words, the probability that we'll get it right if you're diseased is 99%, and the probability we'll get it right if you're healthy is 99%. So in this case, suppose that you get a positive test. What's the probability that you actually have the disease? You can consider two different cases. One, in a general population. In other words, in a population where there's a very small chance that you have the disease. Another one you can consider is a case where 10% of people have the disease, so the disease is much more prevalent. Let's look at how that changes your positive predictive value. So in the general population, remember, we only have about 1% of the people that have the disease. So there are only 100 people in this column that have the disease. But there are a lot more people that are healthy. Similarly, we have a 99% accuracy if you have the disease. So 99 out of 100 people, at 99 out of these 100, are correctly called diseased. Similarly, among the people that are healthy, we get 99% right, so 98,901 we call healthy when they really are healthy. That's 99% of the time. But suppose that we wanted to know, if you got a positive test, what's the probability that you actually have the disease? So let's look at this for a second. So you say, suppose you actually got a positive test, that's this first row right here. What's the probability that you actually have the disease? So that's the number of people that actually have the disease among the total number of people that had a positive test. So that's 99 divided by 99 plus 999. So it's only a 9% positive predictive value. In other words, if you got a positive test, it's only about a 9% chance that you actually have the disease. What's the reason for that? The reason is 99% of a small number, so 99 out of 100, is still smaller than 1% out of a much bigger number. So 999 out of a much larger fraction that are actually healthy people. If instead we consider the case where 10% of people are actually sick, then you have a much larger number of people that are actually sick, and 99% of the time we'll get it right, so 9,900 of people that actually are sick will call sick, and only 900 of the people that are healthy will we call sick, and so then things work out how you'd expect them to. In other words, 9,900 out of 9,900 plus 900, so that's this number in the top left-hand corner divided by this total row, is 92%, and so you have a high positive predictive value. What does this mean? If you're predicting a rare event, you have to be aware of how rare that event is. This goes back to the idea of knowing what population you're sampling from when you're building a predictive model. This is actually a key public health issue, so you've probably seen it in the news that there's been questions about what's the value of mammograms in detecting disease and detecting the value of disease versus detecting cases that aren't necessarily life-threatening. Similarly, you've probably heard about it for prostate cancer screening. In both of these cases, you have a fairly rare disease, and even though the screening mechanisms are relatively good, it's very hard to know whether you're getting a lot of false positives that are as a fraction of the total number of positives that you're getting. For continuous data, you actually don't have quite so simple a scenario where you only have one of two cases and one of two types of errors that you could possibly make. The goal here is to see how close you are to the truth. And so one common way to do that is with something called mean squared error. And so the idea is you have a prediction that you have from your model or your machine learning algorithm. And so you have a prediction for every single sample that you're trying to predict. And you also maybe know the truth for those samples, say in a test set. So what you do is you calculate the difference between the prediction and the truth. And you square it so the numbers are all positive. And then you average the total number of total distance between the prediction and the truth. The one thing that's a little bit difficult about interpreting this number is that you've squared this distance, and so it's a little bit hard to interpret on the same scale as the predictions or the truth. And so what people often do is they take the square root of that quantity. So here, underneath the square root sign is the same number. It's just the average distance between the prediction and the truth, and you just sum it and square it. And then you take the square root of that number, and that gives you the root mean squared error. And this is probably the most common error measure that's used for continuous data. So for continuous data, people often use either the mean squared error or the root mean squared error, but it often doesn't work when there are a lot of outliers or the values of the variables can have very different scales because it will be sensitive to those outliers. So for example, if you have one really, really large value, it might really raise the mean. Instead, what people use is often the median absolute deviation. So in that case, they take the median of the distance between the observed value and the predicted value, and they do the absolute value instead of doing the square of the value. So again, that requires all the distances to be positive, but it's a little bit more robust to the size of those errors. And then sensitivity and specificity are very commonly used when talking about particularly medical tests, but they also are particularly widely used if you care about one type of error more than the other type of error. And then accuracy, which weights false positives and false negatives equally. This is an important point if, again, you have a very large discrepancy in the number of times that you're a positive or a negative. For multi-class cases, you might have something like concordance, and here I've linked to one particular distance measure, kappa, but there are a whole large class of distance measures, and they all have different properties that can be used when you have multi-class data. So those are some of the common error measures that are used when doing prediction algorithms.